Hello everyone, welcome to the lecture 17 in the course Diffusion in Solids. Last class we talked about the atomic mechanisms of diffusion. So, how actually diffusion is taking place inside a crystal, what are the atomic movements, characteristics and so on. And towards the end we briefly introduced to what is known as the correlation factor, which means that the motion of atom inside a solid is not truly random motion. There is some kind of a correlation that exists. So, in the next couple of lectures, we will devote some more time to understand this correlation effects, and we will see what is the concept of the correlated walk and what is the effect of mechanism on this, and these are the keywords that we are going to refer. So, we saw that the expression for the mean square displacement can be written as n lambda square 1 plus 2 by n double summation average of cos theta ij, where cos theta ij represents the cos of angle between the ith and the jth jump. Now, if it is a truly random walk, then the average of cos theta ij is equal to 0. Remember, it is for n number of particles where n or atoms where n is very large. Now, if it is not a true random walk, then the average of cos theta ij is not equal to 0, and therefore, this term is written as f, which stands for the correlation factor. So, this f equal to 1 plus 2 by n double summation of average of cos theta ij is what is called as correlation factor, and therefore, the d star, the tracer diffusion for example, is written as f into d random, which is the d which would have been arisen due to the complete random motion of the atom. F, as I said, depends upon the atomic mechanism and the crystal structure. Now, let us think a little bit what is meant by a not a true random walk, and then later on we will also see how does F depend upon the atomic mechanism and the crystal structure as well. Before we go to understand the concept of not a true random walk, since we already introduced ourselves to the Scilab. Okay. So, for example, I have written here that average of cos theta ij is equal to 0. You can actually write a code in the Scilab and see that whether it really goes to 0 or not. Remember that average of cos theta ij goes to 0 when n is large enough. Okay. For example, if we consider only 2 jumps, where let us say cos theta for the first jump is minus 1, for the second jump is half, then the average will actually not be equal to 0. So, the average of cos theta goes to 0 when the number of jumps is large, and you can write a nice code in the Scilab to actually illustrate that. I will show you the code here, you can try to run it. Okay. So, basically this code generates random numbers, you can see between minus 1 and 1, which is the range of the cos theta. Okay. And then for different n values, that means different jump numbers, here you can see 1, 5, 10 up to 5000, we try to calculate the average of this cos theta. And then when you plot it, the average of cos theta versus the number of jumps, you will see that the plot looks something like this. So, you see that as you increase the number of jumps, the plot actually tends to 0. So, it is very close to 0, or it is almost 0 as the number of jumps increases. So, you can try to write the code yourself, or take it and try to run it. You can also do it for more number of jumps and so on. So, now moving ahead, what is meant by not a true random walk? So, the true random walk actually implies that the jump probabilities of atoms do not depend on the direction of the preceding jump. Okay, so suppose if an atom has made one jump, where it jumps next is completely independent of the first jump. That is the true random walk. However, if the jump probabilities depends upon the direction of the preceding jumps, then it is known as a correlated walk, or it is not a true random walk. Let me try to give you an analogy to understand this slightly better. Suppose you have a room full of chair at an instant, and where this person enters this room, and the only task given to this person is occupy as many times the vacant chairs as possible in a unit time. Let's say some unit time you give to that person. Now you see that this person has so many options. Okay, he can go to any of this vacant chair. So let's say at the next instant he has chosen to be at this particular chair. Still, if he sees around, he has a lot of vacant chairs near to him. So at that next instant, he chooses this chair. So he is now on this chair. Again, he has so many options, so many vacant chairs where he can go to, right? So he goes to this vacant chair. So everywhere he wants to go, he has a vacant chair available. That means the probability that he will occupy a particular chair is same in all the directions. Okay, because you have availability of vacant chair everywhere. This is what is known as a true random motion or true random walk. Of course, when we talk about atoms, we are talking about a very large number of sites and very large number of atoms. But here it's just an analogy to show. Now, imagine taking the same example forward. Now, this person in blue is not alone, but he has entered with 4 other people. Now, the same task, that occupy as many vacant chairs as possible in a given amount of time. Okay, the task is only to occupy the vacant chair. Next instant, again exchange with the vacant chair, again exchange with the vacant chair, and so on. So at this instant, he occupies this vacant chair. And now you see that he has vacant chair not everywhere available. This is occupied, this is occupied, this is occupied, this is occupied. So what is the best option if he wants to keep on continuing exchanging his position with the vacant chair? He can simply go back to the chair which he left vacant, which he can occupy very fast. So the probability that he will occupy this chair is now much more. So he will occupy this chair again. Again he has left this chair vacant. So he can jump back to this chair. So you see that now the direction of the jump here or the direction of the jump here is related to the previous jump. The previous jump, he has vacated this chair. So he is very likely to occupy this chair again, so that he continues exchanging the position with the vacant chair. In a similar way, when you have the vacancy mechanism operative, I will show you a couple of slides later maybe, that when an atom jumps into a vacant site, it leaves a vacant site behind. So the probability that the atom will jump to that vacant site is much higher than the probability of atom jumping to any other site. So this type of walk is known as a correlated walk. Now let us look at the correlation factor for some different mechanisms. First, let us start with the interstitial mechanism. So interstitial mechanism, especially if you consider a dilute interstitial solution. Now the interstitials are available everywhere in the lattice, the interstitial positions I mean. Okay. And now let's say an interstitial solute occupies this position. Everywhere around, if it's a dilute interstitial solution, then it has a high probability of being surrounded by empty interstitial sites. So it can jump here, 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 here. So even if it makes a jump here, again it will find several interstitial sites around itself for the jump to occur. And therefore, all directions for the jumps to the neighboring empty sites are equally probable and independent of the prior jump. And therefore, the average of cos theta I plus j in this case is equal to 0. And in this case, therefore, the correlation factor is equal to 1, because here the solution is a dilute interstitial solution. So, the solute has a high probability of finding vacant interstitial sites around itself. Now, if they are concentrated solid solutions such as hydrides, nitrides and carbides of some metals, then the concentration of the interstitials is large, and therefore, not all the interstitials are available for the solute to make a jump. In such a case, again, like I showed you in the previous analogy, once let us say this atom has jumped, then it has left an interstitial site empty here. So, the reverse probability increases, and therefore, the F will be less than equal to 1. Now, consider another interesting case of interstitial C mechanism. Remember what happens in interstitial C? Interstitial C means when a parent atom itself occupies a interstitial position. Now, interstitial C mechanism, how it progresses is, for example, a tracer atom here is, remember it can also be illustrated for self diffusion, but then it is very effectively shown when we take a tracer example. So, tracer example here, if you see, then let us say the tracer occupies an interstitial site. Now, equal probability exists that it can exchange a position with any of these substitutional atoms, because here there is no preference, it can go to any of the direction. Now, when it goes to the substitutional site, it knocks one of the atoms to the interstitial position. Now, what happens is that tracer wants to come back to the again the interstitial site which has left by its previous jump. Okay. And again then when it is at interstitial site, it has equal probability of displacing any of the substitutional atom and going back to the substitutional site. So, there are the sequence of the steps, if you write, then it is the tracer is going from interstitial site to a substitutional site. Here A denotes the tracer atom. Then again it is going to the interstitial site, again going to the substitutional site, again going to interstitial sites, and so on. Now, if you see this step, when this tracer is at interstitial site and it jumps to the substitutional site, there is no preference. Okay, the probability of jumping is equal in all the directions, and therefore, this particular sequence, which is AS, AI and AS, is a uncorrelated sequence where average of cos theta is equal to 0. However, the sequence where it goes from substitutional to interstitial, then that is a correlated sequence, and the cos theta is average cos theta is not equal to 0. So, overall if you write F is equal to then you can write it as 1 plus average of cos theta, where cos theta is the average of cosines of the angles between pair of correlated consecutive tracer jumps. Now, we come to a very important mechanism, which is the vacancy mechanism. Now, to understand the correlation factor here, you see here, for example, this is a tracer atom, this is a vacancy, and now because we have already seen that the vacancy concentration is not very large in metals. Okay. So, vacancy will approach a tracer atom with equal probability from any of its Z neighboring sites. The probability for a vacancy to jump any of its 1 by Z neighboring sites is 1 by Z. So, it can jump to any of these neighboring sites. The probability is depending on the coordination number. Immediately after a first vacancy tracer exchange, that means once this exchange is done, the vacancy is in a position which permits a reverse jump. Okay. So, immediately once this tracer has gone to this vacancy, where does it find another vacancy? It finds a vacancy immediately in the opposite direction of the previous jump, and hence the higher probability of reverse jump exists. Okay. So, remember, you may say in that case always it will go back and forth, but it is not the case, because there is a possibility that this vacancy and the this atom exchange can also happen. So, that probability is also there, but as far as the tracer is concerned, it will have a higher probability of making a reverse jump. So, consecutive pairs of a tracer jump in opposite direction lead to no net displacement. So, if the tracer moves back to the previous position, then it means that effectively these two jumps produced no net displacement, and therefore you see that the previous expression you saw that the retracer is actually less than the truly random diffusion coefficient, because there are these jumps, the pair of jumps which cancel the displacements, and therefore the effective distance to which the atom has diffused comes down. So, the backward correlation effectively cancels the pairs of tracer jumps. Therefore, if you want to write the effective number of jumps is actually equal to n into 1 minus 2 by z. So, tracer made n number of jumps, but the jumps which actually caused a net displacement are reduced by a factor of 2n by z. And the correlation factor therefore is written as f approximately equal to 1 minus 2 by z. So, here are the correlation factors given for several of the structures. So, you can see, for example, honeycomb structure, then 2D square, 2D hexagonal, diamond, simple cubic, BCC, FCC, FCC also. So, you notice a couple of things here. For example, here if you see from here to here, the mechanism of diffusion is a vacancy diffusion, but depending on the crystal structure, the correlation factor can vary from 0 to as high as 0.78. which tells you that it is not just the mechanism, but it is also the structure on which the correlation factor is dependent on. Similarly, if you consider, for example, FCC here, in FCC case, when you have a vacancy mechanism, then the correlation factor is approximately 0.78. When you have a divacancy mechanism, then the correlation factor is 0.45. So, for the same crystal structure, you have a different correlation factor depending upon what is the mechanism of the diffusion. So, both the mechanism and the crystal structure play a role here. So, for example, again in CaF2, now which in alloys, for example, if you see that CaF2, when you talk about the fluorine diffusion, it is non-collinear interstitial C. So, you have a very high value of correlation factor. In CaF2, when calcium is diffusing, depending on whether the interstitial C mechanism, the diffusion is happening in a collinear way or a non-collinear way, the correlation factor can change. So, sorry. So, again you see that slight differences or slight variations within a diffusion mechanism itself can cause or can lead to a change in the correlation factor. Okay. Now, in the next class, we would look at how do we calculate these correlation factors for some structures. We will demonstrate for one or two, and we will also talk about a little more detail about this correlation factors. So, see you for the next lecture. Thank you.